Okay. So, welcome everyone. Welcome from me too. So we're going to have a brief lecture on computational chemistry. Now, obviously, we're not going to have a proper introduction in computational chemistry. It's going to be very selective, very objective, superficial here and there. We're not going to talk about formalism all that much. It's just like wandering around some topics that might be useful to you for the summer school. Just so that you know, you're going to get all lecture notes from all the slides from everyone. Okay. Afterwards, they will be uploaded somewhere. They're not uploaded beforehand because in some cases they're not fully prepared. In other cases, we're using some images that we cannot distribute, so we're using them here, but we will have to change them perhaps for the uploaded material. So let's see. What are we going to do here? Frank already mentioned major points about the school, the ideas in the school, and what we're going to be combining. So what we're going to be doing here is we will have some lectures on spectroscopies, and some of these lectures we will also be introducing computational methods, so some of the theory, and then we're going to have practicals, which can be computational practicals like with ORCA, or it could be practicals where you will be using pen and paper and solving things. Or you will be using programs to simulate spectra. So you will be understanding how specific parameters that relate to specific spectroscopies are used to simulate spectra. There will also be tours of the labs, but in general, when it comes to many of the practicals, there is significant emphasis on using quantum chemistry to reproduce spectroscopy. Or actually, what we want you to get a feel of is how quantum chemistry, how computational chemistry can be, in principle, incorporated into actual projects, into actual research, so that then you can more easily, when you go back to your lab and you have a project to do, you might be thinking about, okay, how can I do that? How can I extend, enrich my project? So I suppose you know what spectroscopy is. Okay, in most of the cases we're talking about interaction of electromagnetic radiation with matter. We measure this interaction, we try to understand this interaction, we have some observables. Sometimes we use them as they are, sometimes we do something, okay, with the data, and then we extract specific parameters. So for example, from an EPR spectrum, okay, we not necessarily read all the spin Hamiltonian parameters, but we can fit the spectrum and deduce some parameters that fit to a specific framework, like spin Hamiltonians. And there are, or we want to use the rules that govern experimental observations, and we want to make connections with quantum mechanics. So we have all these different forms of spectroscopy, and we will actually be covering almost everything, if not actually everything. There will be absorption spectroscopy tomorrow, UV-Vis, XAS, IR. We will be having lectures on EPR and Endor and Most Power. And at the same time, we will be talking about how to use, how to connect these with quantum chemistry. So I'm not going to go over the program again. You all have it. You've seen it. So what can we expect? Okay, just coming back to the original question. What can we expect from spectroscopy-oriented quantum chemistry? So first of all, and that point came up, it should not be a way to decorate an experimental paper, because that's also pointless. And that even if it looked like something valuable a few years ago, like reproducing an IR spectrum today by DFT, it's no longer valuable, and nobody can actually consider it like a valuable contribution to the paper. You do not learn anything. It should rather be a source of insight. So what it means is that you're not obliged to use quantum chemistry unless you find like a proper way of using it so that you can obtain some insight, so gain some value out of it. But at the same time, you should know that doing computational chemistry or doing quantum chemistry, which is like using quantum mechanics for something, it does not have to provide a unique and definitive answer to any of the questions that you ask. Rather, it can be useful if it helps you understand something, or if it helps you think about possible interpretations, or if it helps you come out with a series of possible interpretations. And that's already something very significant. That also means that the point is almost never reproducing a number, because you not necessarily learn something about reproducing a number unless this is part of a bigger effort. In the case of computational spectroscopy, which is most of the use of computational chemistry in this school, the point is to use applied quantum mechanics to compute spectroscopic properties. These are not necessarily full spectra. For example, we're not going to like compute a whole EPR spectrum or something. Like, we're computing specific aspects of the electronic structure that we can connect to experimental observations. And we can also use quantum mechanics in ways that are complementary to the spectroscopy that is performed in an experimental study. But in general, like a principal kind of guideline in how we use computational spectroscopy also in the school is that we're trying to connect structure with properties and structure with function. And properties include like all sorts of spectroscopy. That's really the fundamental aspect. Molecular structure and whatever observable that would correspond to a structure. So just taking a broad view of computational chemistry, like this is like a broad term that includes many different things. There is no specific kind of definition of computational chemistry, or some people will use computational chemistry versus theoretical chemistry versus quantum chemistry in different ways. In general, there is a kind of subfield, all overlapping, okay, of computational chemistry that deals with the fundamental theory, like the quantum mechanics, for example, or the molecular mechanics, or whatever. And there are people, so one might think about this as activities in a sense, not just specific fields. There are people then who worry about the development, like implementing, writing code, or making the code faster, or make it run on different platforms or whatever. And then another part of the activity is, let's say we have a theory, someone implemented it, we have a code in Turbo Pascal or whatever, and then we need to know if it's useful. Okay, so we need to know if it works. So there is an activity that is kind of very special for computational chemistry. It's benchmarking. We don't really have this kind of benchmarking in other fields of science. Okay, it's something that can be very extensive for computational chemistry, where there is like there's a whole effort, and one could just do like for a career, like only benchmarking. So how to have specific data sets, and how to test specific methods, and then how to go back and tweak the methods to reproduce either higher level results or experimental results. And then we have a very open-ended field of applications. So in the case of theory, development, implementation, you have obvious connections with physics, mathematics, computer science, computer engineering, benchmarking in something kind of unique. And then applications could involve anything. Right? It could involve like anything, because applied quantum mechanics or molecular quantum mechanics can actually be used in all sorts of fields of science, from astrochemistry, astrobiology, biochemistry, obviously, you know, materials, whatever. I mean, there's no end there. But there, it's where we need to kind of know both, right? We need to understand how to use computational chemistry, how to use quantum chemistry, and we need to know, for example, something about proteins, if our systems are enzymes, and something about spectroscopic methods used for study of proteins. So we have the programs, we have the benchmarking, and then we have the applications, and we're mostly interested here on applications. By applications, I mean not just running a calculation, I mean projects that have this specific feature. You ask questions about the world, right? You don't ask questions about how do these functionals compare. Okay, that's not a research question. Which basis set is better? That's not a research question. Okay, a research question is something that is a standalone question, like regardless of what method, computational or experimental, you will use to address it. Okay, so why this catalyst works and the other doesn't work is a valid like research question. Then you can do experiments, you can do theory, you can do whatever. That's what I'm talking about. So now, to use calculations, what are we actually doing? We're simulating things. We're using simulation, and that word has a rather specific meaning. Okay, I'm not talking about solving equations. I'm talking about simulation, which means that we have some part of the world, and we want to reproduce it, to represent it computationally. And then we want to imitate some properties of these real physical systems that we represent computationally. So that's a simulation. And that could be done in a huge scale, like we want to simulate some fluids, whether that's the atmosphere or there's something tiny, or we want to simulate a chemical system. But the goal is just to represent something in a computer. We have an abstraction, and then we want to act on this abstraction so that we can compute properties, whether this is structure or whether this is whatever observable. And we are going to do that so that we can then understand how the real system behaves. So in this context, we need to make some distinctions. So you are in the lab, you have your sample, you have a setup, an experimental setup, or you're using some method and you're doing an experiment, you're measuring something, and you have your measurement. And we want to do something similar in the computer. So we have a model, we choose a method, so our model is like the representation of the physical system, a molecule, whatever, and we're using some method, and we're doing calculation. And then optimally, we would have an observable, again, computed, and then we can compare it with experiment, and then this fits like an overall research goal. But it's really important to understand that we cannot use any method on the sample, any computational method on the sample. So we will never know what any method would give if we had an exact representation of the sample, because we can never have an exact representation of the sample. And at the same time, we can never really know what the experiment would give for our model. And the reason is that there will always be possibly unknown difference between an experimental sample and our computational model, our representation of it. In some cases, for example, in astrochemistry, you may have a very small molecule somewhere in, and it's sitting there alone. And we know, for example, it's methane or a methyl radical. In that case, then we can be pretty certain that there is minimal difference between our model of a methyl radical and what's there in outer space. But what about a metalloprotein? Right? You will never have a pure metalloprotein in one state exactly in any sample you might ever prepare. And you will never be able to have one observable for one specific state of one protein with any spectroscopy that you will use. And that's not always a problem, okay? Because we need to be clear about this. It's not the goal of computational chemistry to reproduce this inhomogeneous, heterogeneous sample in the computer. It might be that we want to understand how the catalytically active form of the protein kind of works. So it's okay if there is a distance there, but we need to be aware of these facts. And we need to be aware of how we combine, all this in a single project. So then we can be talking in general about fidelity in our model. So how faithful is the representation we're using in the computer to the real system? And now the question, what is the real system, is also a bit problematic. I mean, it's not always obvious. When you have a molecule and you're performing an experiment on a crystal, what is the system you want to model? Is it the crystal, or is it a molecule in the crystal? When you have something in solution, what is your model? What are you probing spectroscopically? This molecule that you have in solution, or the molecule solvent system? So that's also a question we need to address. But in any case, fidelity could be defined as how close we are in our representation to the sample, perhaps, or to what we consider to be a legitimate representation of the chemical system. And then we can be talking about the accuracy of the method. And the accuracy of the method, again, it's like, what are we talking about when we're talking about accuracy or precision in computation? For a sufficiently complex system where we have to even decide, like, what is the system really, then that's not always obvious. For example, you can do many measurements and you can get like a range of results, okay? And then you can decide that this is the precision. Or you may know the result, and then you can talk about the accuracy. But you can repeat a quantum chemical calculation 1 billion times, and you will have to get exactly the same answer to an arbitrary number of decimal digits. So what is precision there? And this is important to know, because very often people with a strong experimental background might ask, okay, so what is the uncertainty in this computed value? Well, does that question always make sense? It might not, because it refers to something else than the traditional concepts of precision and accuracy for experiment, and because we also do not know the exact experimental value for our computational model anyway. What do we mean by a model? Normally, in most cases, we simply mean the representation of a molecule in space. So a list of coordinates and a list of atoms that define whatever the nucleus is, for example, that's a model. And that's many times sufficient to describe what we're working on. So in this case, we're working on this molecule, and that's its representation. That's our model. When we're doing quantum chemical calculations, we also need to know how many electrons you have, what is the total charge, and other things. So we give some extra information. Like, for example, here we have like the charge and the spin multiplicity. That's useful information. But overall, that's what we mean often by a model. So we would need to constantly be thinking about what is a good model and what is a high fidelity representation of a chemical system that interests us. And like, before we proceed to the methods, I will just want to mention a couple of things about where we get the models from. I mean, you can use a program to design the models, or you can use crystallographic data. Maybe you have some crystallography on some models, on some molecule, okay? No matter what we do, very often, or typically, you can never use a crystallographic model, which is in itself a model, okay? It's not primary data, it's an interpretation of data. So you can never use a crystallographic model directly and turn it into a computational model. You always have to work on it, because They might be the most typical, it has no hydrogens, or they were positioned by some automated algorithm and the carbon-hydrogen, for example, bonds are really weird, and you need to correct that. Or there are multiple conformers, so you see weird things in the crystal, and you need to correct that. So whatever you input to a quantum chemistry calculation needs to be perfect and pristine and exact, otherwise it makes no sense. So you cannot have like two overlapping phenyl groups, for example, and wait for some calculation to correct that. It needs to be perfect. Whether this means that you decide on one model or several possible models coming out of the crystal is something that you need to decide, but they need to be pristine. And that is, based on our experience, like hearing from people who are to start using ORCA, for example, to do some calculation, whatever calculations, that's something that is a very common trap. So they have some structures, but they have not made them perfect before running calculation, then something happens. Okay, and it's usually because the structure was not like, it needs to be really good or chemically correct. So if you have a carbon that has no hydrogens, like weird things will happen, all the calculations will not work, and there's nothing you can do unless you initially put the carbons and then you proceed. With protein crystallography, like if you're doing like metalloenzymes and you actually want to work with that's a crazy situation, and you need to be very careful, and you need to train yourself in all the steps that are necessary for preparing a model of an enzyme or a protein or whatever for calculations. And there are all sorts of things that can go wrong there. There are all sorts of incompleteness and problems in protein crystallography, and you need to be aware of that, and you need to do something about this. Unfortunately, although we have been working in my group also with lots of proteins, metalloproteins, like huge systems, and we are well aware of the complications and of how much effort you need to spend like before you do the calculations just to make sure you have a proper system. And many people have tried to automate this, but the reality is that so far you can automate simple steps, but you cannot really automate everything. So you just need to be aware of the problems and deal with them. Some notes about the environment. Like I already mentioned, like we want to model something, a molecule. We want the spectrum of a molecule, absorption spectrum, whatever. But what if we want to ultimately compare with experiment? Then was the molecule in a solvent? Most of the times it is. So do we need to worry about the environment, which could be the solvent, could be something else. It could be like a protein matrix, it could be like a moth, whatever. It's something, there is an environment. Do we need to worry about this? Now, that's a decision that you have to make based on your understanding of the chemistry of the system. Okay, no calculation, no program will suggest something about this. But it is important to consider that solvent can drastically affect what you compute, because the solvent, through all these physical effects that are listed here, can affect the electron density of the molecule, if we consider like the molecule as a separate entity, could affect its geometry or its conformational preferences, could affect the excited states, all sorts of spectroscopies, reactivity, and so on. I mean, you already know that, okay? I mean, we have the solvatochromic shifts, for example. So if you want to compute an absorption spectrum and you know that the molecule has been in a solvent or been measured in a solvent, then you know that different solvents will shift the spectrum. So you need to do something about this. So your model is not the molecule, is the molecule and whatever you decide to do about representing the solvent. So in the simplest case, we have some sort of continuum dielectric. So we don't actually represent the molecules of the solvent. And we have different algorithms, different ways of making like a cavity for our molecule, which could be like a very simple or more elaborate or whatever. And then there are additional algorithms that will smoothen kind of the surface, and we will have some energetic contributions from the solvent. And there are standard models like CPCM or SMD that do a very nice job in representing like electrostatic effects of the solvent, mostly. But we also know, okay, that there are cases where that's not enough. For example, you may have come across already in NMR. Okay, you have some signals in NMR, and you know that something happens sometimes when you have a coordinating solvent, right? So then you actually need the solvent to be present as a molecular representation. Or you may have some chlorophyll or some heme or whatever, and then in some solvents, okay, in some solvents you will have axial coordination. So then your molecule is no longer the heme, is no longer the chlorophyll. Your molecule is something that has a coordinated solvent. So once you decide, based on experimental information or your knowledge of the system, that a continuum solvent model is not enough, then you need to represent the solvent explicitly, whether it's just one molecule or just many molecules of solvent, which then creates its own questions, like how do I position them, how do I sample this, and do I need to do molecular dynamics or just a random distribution of molecules? Do I need to worry about, like, okay, I'm putting like 5,000 molecules of water, like what's supposed to be like the density of this thing, like the way. So there are other considerations there, and that's not a simple matter. But in any case, we're not going to deal with this at the summer school at all, just something to be aware of. There are some very nice examples in the literature where people have studied systems, and the answer to a seemingly puzzling question was simply that it was the solvent, or it was like the environment. So this is an example taken from the literature, from the work of Marius Radon, and it addressed a question about the sextet-quartet transition energy of this hydrated iron. Okay, and there were papers debating about like the accuracy of different ab initio methods, and maybe the experiment is wrong, or maybe the interpretation is problematic, or maybe there is like something very weird about the electronic structure. And then what the people in this paper showed, it was like, actually, well, if you take like a second sphere of waters, then the first sphere changes sufficiently so that then the answer is correct. So the problem there, and this debate in the literature was not really in this view about the methods that were not giving the right answer. It was about like the model was incomplete. So an iron with 6 water molecules is not a good representation of iron in solution in water. And we see it in other cases, so specifically this about the hydration. So we had a study on redox potentials of first-order transition metal ions. And if you do not have sufficient amount of explicit waters, you get results that are drastically shifted from what is expected. So specifically, another case that I already mentioned was about coordinating solvents, which is often crucial for spectroscopic investigations. Of course, another different point that should be mentioned here is what if the environment is a solid? Okay, so that's a bit more tricky. But what is in that case very clear is that having just a part of the solid extracted and doing calculations in it, that's not even like a poor approximation. It's like it's something else entirely. So in that case, you need to worry about the embedding, which can be done in different ways. Some of these ways are described. Maybe they will be mentioned in the summer school. I'm not sure about that, but they are described in literature from the group. And for metalloy enzymes, it's pretty obvious that you have 2 options. Either a cluster model, where you say that my active site or whatever group of interest is like a molecule, and the rest is just a spectator ligand that I can ignore. Or, you need to include everything, and then that's typically done with multi-scale models. So I will first talk a bit about molecular mechanics. Okay, that's not quantum mechanics, that's molecular mechanics, because I think that connects a lot with our view of molecules. So how do we represent molecules? So that's a chlorophyll. Okay, this is just some lines. I could have some carbons, but we have agreed that when I don't put anything, like it's a carbon. So that's a representation of the molecule. But that's not really like satisfying in terms of creating a model. Okay, and when we're thinking about a model, we're thinking a bit more about something that actually has a very specific three-dimensional structure. And how do we present it? With balls and sticks. We could do just sticks if it's a bit of big molecule, but I think I have used questionnaires in the past, and I know that most people find the ball and stick representation kind of more intuitive or more precise for whatever reason. Of course, we can also agree that we're going to use some weird representations like this, where we agree on specific visuals that represent kind of higher order structure, but we are comfortable in the idea that, you know, behind this there are balls and sticks, just too many balls and too many sticks to show. But why would this be like a normal representation of a molecule? Is it something that we as scientists find like proper, or is it something that we just learned from school? Like that's the figures of the molecule. Why would not something like this, without the molecular skeleton of balls and sticks, why would not that be like a proper representation, a better representation of a molecule? So the point here is that we have been, we have learned, or we have been conditioned, or we instinctively find specific representations of molecular structure kind of easy to understand. Okay, and this representation, this mental image we have of molecules is of atoms as objects connected with something. So our intuitive picture of molecules is a classical picture, is the picture of molecular mechanics. That's our intuitive. No matter how many, you know, high-level quantum mechanical calculations we can do on a molecule, eventually, if we want to say, I did this on that molecule, we're going to draw something that is purely like a classical abstraction. So in classical mechanics, the fundamental objects are atoms, something called atoms. Okay, now think about this. These are not the quantum particles, so we're not talking about nuclei and electrons, we're talking about something called atom. And then these atoms interact somehow. So, in molecular mechanics, because we have atoms, and we need to describe a molecule composed of atoms, if we think about a carbon atom, okay, it's not a unique thing. A carbon atom or a carbon without specification in an aromatic ring is different than the carbon in methane. So in molecular mechanics, we have atom types. So we have several different atom types for each element. So we can have an sp2 carbon, an sp3 carbon, an sp carbon. We can have a carbon type that is part of an aromatic ring. We can have a carbon atom type that is part of something else, where it's doubly bonded to an oxygen. So we have these atom types, and these atom types have some features, like mass, partial charge, van der Waals radius. And then we have some parameters reflecting how these different atom types, all sorts of pairs that can be made of atom types, interact. And these parameters and these properties of the atoms and the parameters describing the interactions are typically fixed. So when we take all these parameters and all the formulas that are used to describe the interactions, we have what is called a force field. So in the case of a force field, we are describing the energy in molecular mechanics as the sum of very specific, very understandable terms that have very simple forms that I'm going to show you. So a force field, when we say I'm using a force field refers to the form of the equations. We have a list of whatever, 6 equations. I have 6 equations, and I have a list of parameters and atom types, and that is the force field. And I can use that to do simulations, to run something. Now, what can I do with this? We're going to say in a moment. And there are different types of force fields that we can use in molecular mechanics. Now, the energy expressions can be something very simple, using a simple potential form for a bond. So for 2 atoms, I decide what is the R0, like the equilibrium bond length, and I can decide how stiff the potential is. And so on for the similar for the angles, or dihedrals that describe how bond can rotate, 2 groups can rotate. In some cases, I can have parameters for improper dihedrals, which is something that restricts how an atom can deviate from planarity. And I can also have some terms describing non-bonded interactions. So van der Waals interactions, and I can pick some sort of formula for this, and I can decide how I combine the parameters for different atom types in these formulas, and I can have the simple Coulombic interaction, and that's it. I mean, these equations define the force field. What can I do? I might be able to do conformational search. I can represent my molecule, I can assign atom types to the different atoms in the molecule, and I can use these expressions and their associated parameters to, for example, scan some sort of potential energy surface and find different minima, for example, different conformations. And I can also have relative energies that are deduced from these expressions. So there are different types of force fields for different applications, for proteins, for lipids, for different solvents, whatever, and they're usually fitted or trained, as is more typically said today, on experimental or more often on computational results. So you may have potential energy surface or whatever, and you use that to fit parameters. You might have, or you might come across in the future, if you don't have come across already, machine learned force fields. These are listed here, but they're actually something a little different, because they resemble in many ways conventional force fields, but they're not constrained by a specific set of equations that we give. Okay, they can, through training, some models can come up with their own internal representation, internal equations, sort of. What we can do with molecular mechanics is treat extremely large systems, and they scale extraordinarily well, and we can represent big molecules like proteins, and we can do simulations that are completely crazy, like whole cells, and so on. And we can use them in molecular dynamics, so we can introduce some temperature in the system, some forces, and we can do simulations that are really, really useful for large-scale questions, particularly. So we can address very important problems. For example, here in biochemistry, but overall, generally speaking, although there are exceptions here and there, we have limited ability to describe chemical processes because we have predefined bonds in the majority of cases. So, for example, we cannot easily study reactivity. And there is limited transferability. There are force fields for specific classes of compounds or types of chemistry. And we cannot have something that is completely universal in the classical construction of force fields. And then we're talking about transition metals in this school, and transition metals are just like, they are crazy. You can have force fields for a specific transition metal in a specific oxidation state, like manganese 3. Okay, and you can make the force field describe correctly the Young-Taylor distortion even. But that's it. So you can apply it for manganese 3 compounds that have an axial Young-Taylor elongation specifically. And that's it. So they are not very useful in spectroscopy of transition metal complexes. Because for the spectroscopy of transition metal complexes, we mostly need to worry about electrons. So we need to talk about electrons. So we need to have this sort of view of what electrons are doing. However, molecular mechanics are still very, very important in dealing with biomolecular systems like enzymes, like proteins, where we are interested in cofactors, whether they are active sites or pigments or whatever, and we need a proper representation of the environment. So there, QMMM methods are crucial. For example, there are many cases where it's not even possible to reproduce redox potentials of cofactors that participate in electron transfer unless you have like a very good representation of the electrostatics of the protein matrix. So to do that, we use QMMM methods, which means that we decide, it's our decision, like what should be the QM region, what do we describe with actual quantum mechanics, and what do we represent with simple force fields. And then we have different types of coupling, okay, between these two regions. We can either treat each subsection separately and then just decide how to couple them, or we can have a scheme that is actually a bit more straightforward in many cases. We can have a subtractive scheme where we treat the whole thing with a force field, and then we treat the region of interest with quantum mechanics, and then we try to subtract the two, so we are left again with kind of the joint description. In these methods, what is really, really important and very often difficult or ill-defined is to decide what to do and how to treat the interaction and like the region where these two, where the QM region terminates and the MM region starts. And this relates also to the sort of embedding that we're doing. So these are also called embedded methods. And we can have a simple mechanical embedding where simply the QM region is kind of fixed through like mechanical forces, let's say. Or we can have electrostatic embedding, which is in many cases like the minimum you should do. And it is very often essential even for studying not spectroscopy necessarily or in all cases, but even like simpler aspects of the system. But also for spectroscopy. Imagine, for example, you have excited states that have charge transfer character and you're studying a metal cofactor in a protein. So your calculation of excited states will be drastically, critically determined by your representation of the electrostatics of the environment, as a simple example. The treatment of the boundaries across covalent bonds is a sensitive issue also in setting up QMM calculations. And often we use link atoms, and we need to do something about the charges so that we do not overpolarize the QM region. There are a lot of details that one can find in the ORCA manual. So I should say that if you have not noticed, there is something like an ORCA manual that has like I don't know, it's pretty long. Okay, very rich in information, and it's you will find a lot of things there in the manual. Besides just how to use ORCA, a lot of information about thinking chemically about modeling. Now, the problem is, of course, that molecular mechanics like conforms to our view of molecules. Okay. QMMM is really important, so we need to do spectroscopy. To do spectroscopy, we need to use QM. There is actually IR spectroscopy, where if you have a force field that describes very correctly, in molecular dynamics, how a molecule can vibrate, that's probably the only kind of spectroscopy you can do with force fields. But for everything else, we need to worry about the actual quantum mechanics. So there will be formalism in these slides, but I'm not going to actually, talk about the formalism. It's there so that you have everything in the slides. So I will be kind of much more descriptive and superficial here. So you know about the Schrödinger equation. That's what we need to solve. And there is something there called the wave function. And there is a Hamiltonian that contains all the parameters that make sense. Okay, the kinetic energy of the nuclei, the kinetic energy of electrons, potential energies then for the nucleus, electron, and nuclear-electron interaction. So we have like this kind of form of an equation, and it's fine. We know what to do. We need to find a way to approximate the wave function, and then we're in a very good position to know about the energy of the system, and if we have a good wave function, we also can get observables. So then we can also talk about spectroscopy. So our goal is to have some sort of representation of the wave function of the system. And most of the times in our case, we're talking about the time independent, okay, Schrödinger equation. So we leave like the time outside. We're talking about stationary states, and most often we're interested, okay, in the ground state. Okay, then we can see what happens later. But it is also kind of useful to remember that the Schrödinger equation is not like that's everything. Okay, it's something that is the basis for a lot of quantum chemistry. Okay, but there are things missing there. For example, the Schrödinger equation is not telling us that electrons are indistinguishable or that they have spin. The Schrödinger equation is not telling us that there are relativistic effects in nature. Okay, so there are several things that are imposed afterwards or externally. A very useful approximation here is the Born-Oppenheimer approximation. So Max Born and Robert Oppenheimer were very interesting personalities. They might have not agreed that this is their biggest contribution to science or history, but in chemistry, I guess that's what we know them for. So in the Born-Oppenheimer approximation, we just disentangle the nuclei from the electrons. And that's really, really nice and useful, because then we can solve independent equations. Or we can decide that, nuclei, we don't actually want a wave function for the nuclei. We'll just position them somewhere, and we will introduce the position of the nuclei kind of parametrically in the electronic equation. By the way, the meaning of the wave function is that its square represents the density. So we can have this equation, separate equation for the nuclei, but as I said, we can disentangle the two. Now, what is really important here about the Born-Oppenheimer approximation is that, first of all, it makes solving things easier, but it also gets us back to this concept of potential energy surface, which we had, okay, before we knew about quantum mechanics. And that's really, now we can start talking about, we can use ball and sticks again, kind of, sort of. Right? We don't need to worry about how to represent like the nuclei, how to represent the electrons. It's just, the nuclei are there. Okay, and then I have a structure then. Then I worry about what the electrons are doing. So I can represent here, like in the previous slide, if you remember, there were like maybe atomic positions. But here we're talking about nuclear coordinates, the coordinates of the nuclei. And in the previous example, I did not call this a transition state. It was a barrier for some sort of interconversion, because we could not have, it could be a transition state, but only for a conformational change. Here it can be for anything. Okay, we're not constrained. So then how do we solve this? Maybe there are many ways, but we are guided by a few principles. We are guided, first of all, by the variational principle, which is telling us that if we can guess a form about the wave function, something, whatever, and then we can try manipulating it and changing it and see what the energy is. And the variational principle is telling us that the energy, if you have a better representation of the wave function, the energy will be lower. So if we go down in energy, the wave function should be better. And that is a very useful guide. But now, how do we actually write like a trial version of the wave function? So what people have historically found very useful is to go back into steps and write, for example, the wave function of the whole molecule as a combination of simpler wave functions that describe the electrons. So each electron has some sort of wave function. And then to make this work, we actually need to put like the little letters there for the electronic wave functions in a Slater determinant, because, and that's kind of external knowledge, because we know that the electronic wave function, so the wave function for the electrons, should be antisymmetric. So we put everything in Slater determinant and we satisfy, in a determinant, okay? We satisfy this requirement. So these little functions are called orbitals. And when we're talking about a molecule, these are molecular orbitals. So these are the molecular orbitals. And now our task is to, okay, we have expressed a wave function in terms of molecular orbitals. How do we express the molecular orbitals? Like, how should they look like, mathematically, at least? So the solution here is to use atomic orbitals. So this is the linear combination of atomic orbitals. Now this is, again, this is not the only way of doing this, okay? It's just, it works, and it's also intuitive, because we have this view of molecules that are built from atoms. So it's also kind of satisfactory to think that there are atoms and there are electrons kind of the atoms, and they come together to form a molecule. So then this also makes some sort of sense. And now the atomic orbitals are actually, in this context, the basis set that we're going to use in the calculation. The atomic orbitals are the basis set, and these are the components that will be used to express the molecular orbitals. And these are typically Gaussian functions that resemble hydrogenic orbitals. What are hydrogenic orbitals? If you have like a hydrogen atom and you have a nucleus and an electron, you can actually solve the wave function of the electron and have a nice formula. But you can only do that when you have one electron. So then you cannot do that, for example, for iron, okay, because you have 26 electrons. That's a problem. So you cannot have like properly solved atomic orbitals for iron. You can have atomic orbitals which are called hydrogen-like orbitals when you are dealing with iron 25 plus. Okay, cool. So these kind of abstractions, or these approximations to atomic orbitals themselves being like an approximate concept when it comes to multi-electron atoms, are used to construct the molecular orbitals that enter in this Slater determinant. And then what we are going to minimize, essentially, and I'm not going to talk about all the different terms here, what we want to minimize is the coefficients. So we keep the atomic orbitals fixed, the basis set. They are what they are. We decided that that's a good representation of the whatever atomic orbitals for each element. And then we're going to change some coefficients that determine like how these are mixed to produce the molecular orbitals. And we have a procedure that kind of optimizes these coefficients until the energy, the total energy of the wave function is the lowest possible. And then it stops. And it's an iterative procedure that is called the self-consistent field procedure, which involves like guessing some starting orbitals. We have defined our basis sets. And then some operators are formed, some integrals are computed. There is a process that you can find more information on elsewhere. And then in this iterative procedure, what we want to achieve is to have the best possible molecular orbitals based on the basis set, the atomic orbitals, in other ways that we provided, so that the energy is the lowest possible energy. And this is the Hartree-Fock energy. And this is the approximate many electron wave function. Now, the molecular orbitals could look like the molecular orbitals, you know, okay, from basic chemistry, like the pi orbitals, or whatever orbitals of whatever molecule that you find in transition metal chemistry, in organic chemistry, like everywhere. I mean, we know, we are familiar with orbitals without doing, you know, Hartree-Fock calculations, without doing quantum chemistry. But these are essentially the same kind of entities we're talking about when we're talking about molecular orbitals here. And we can look at them, and we can connect to concepts, more qualitative concepts perhaps, of electronic structure. And that's where concepts of HOMO and LUMO, for example, come from, and then we can discuss other concepts, more fuzzy concepts of chemistry based on the molecular orbitals we obtain. But it should be clear that that's not a real view, that's not a real description of the world. It's just we made a decision to do our calculations this way. We could have made another decision. Okay, it's just it worked for us, and it felt whatever, reasonable. So they do not exist. It's part of the algorithm. But they're useful. At the same time, they're not unique. So we can transform these orbitals into something else. So nothing will change necessarily. Okay? But they are different orbitals. Like Frank mentioned NBOs. That's some sort of transformation. There's a different set of orbitals. So we can express the same wave function essentially in different types of orbitals. They have different shapes, they have different forms. They may or may not have well-defined energies. So it's just our way of talking about electronic structure and talking about molecules. These molecular orbitals are also typically the foundation for discussing excited states, but since they're not really there, so talking about electrons moving from here to there, like it's already, like it's a very, very approximate way of talking about reality. And it may be kind of close to reality for something like HOMO-LUMO transition, and may not be even good for that. But certainly for higher excitations, that breaks down. Now, Hartree-Fock theory is supposed to be like the fundament of quantum chemistry, and it's fine. It's beautiful. It's an amazing construct, actually. But if we're talking about transition metal systems, like it's pretty useless. And if we're talking about spectroscopy, it's also not very useful for any type of spectroscopy. It can be considered a useful starting point for other kinds of calculations, but all the concepts that we're using here are very useful also for other types of calculations. So all these ideas about the self-consistent solution and the molecular orbitals and everything can be applied almost as they are on DFT. Okay, so about basis sets, just a brief technical overview of basis sets. Like I already said, that basis sets are supposed to be these representations of atomic orbitals, simple fixed equations that we're using as components of a calculation to solve the actual wave function, or to fit molecular orbitals. In reality, in practice, we use more than one function for a given atomic orbital. So for the, I don't know, for the 2p orbitals of carbon, we will use more functions because we want a better representation. We want more flexibility. And the bigger the basis set is, which means the more different functions we use to represent an atomic orbital, the better the more flexibility we built into the molecular orbital representation, and therefore the better the wave function is supposed to be. So that's the task that I mentioned before. And for this task, we're using Gaussian functions for computational expediency, although they're not necessarily better at describing certain parts of the wave function when we compare them with hydrogenic orbitals. But we compensate for this by using more, and because it's cheaper to use more Gaussian type orbitals than other type orbitals, like Slater type orbitals, which might be a bit better in terms of their shape. So to make sure that we have flexibility in the representation of the molecule, whether we're doing Hartree-Fock or DFT or whatever, we want to make sure that the basis set is flexible in the region of interest. Most often that's the valence region. So many types of spectroscopy are concerned with what's happening in the valence region. So we want this region to be better described. That's not always the case though. Okay, you may have some application where you want hyperfine coupling constants of some transition metal ion, and that depends on what's happening close to the nucleus. So a standard basis set that might be considered big for most applications might actually be very small for your application because it's not flexible close to the nucleus. So there are all sorts of different families, and I don't know, there are hundreds of basis sets in any program you might care to look for. They're nothing exotic, okay, basis sets. Sometimes people get confused about this, or they think it's something really weird. It's just a set of exponents and coefficients that correspond to a simple, equation of a Gaussian. And that's it. The more, the higher the exponent, like the tighter the function is, the closer to the nucleus, the lower the exponent, the further from the nucleus they are. And then you multiply this with something else that gives you the different angular momenta, and that's your function, basis function. You might also come across, also in some of the exercises in the school, across effective core potentials, and their job is to replace the inner functions by a single potential, so that it would not treat the electrons explicitly. So we take molecular orbitals out of the picture that are close to the nucleus. That's also one way, an indirect way, to include relativistic effects. Although there are more satisfying and satisfactory ways to include relativistic effects, for example, use some relativistic Hamiltonian, which then, however, needs specific basis sets normally that kind of represent the changes that happen under the influence of relativity. Other technicalities you will find elsewhere and in the manual, and will be discussed also in some of the practicals. Now, there are always questions about what basis set should I use here, what basis set should I use there. And what you will also see from examples during the summer school is that there is no simple answer to this, right? Because it really depends on the system you're studying, it really depends on the property you're studying, and it really depends on the method, like the quantum chemical method that you're using. So, for example, if you want to do some calculations on a gold complex, then gold is famous for relativistic effects. So you need to do something about relativity. And if you do something about relativity, then it means that you need to consider what basis sets you're going to use for the relativistic approach you chose. So if you want to do some sort of relativistic Hamiltonian, then you need to have a specific basis set for this relativistic Hamiltonian. Depending on the method, right? Couple cluster calculations, we'll mention them a bit later, versus DFT. Different methods have different requirements of how big a basis set should be, or what it should contain. Like in terms of higher angular momentum functions, for example. So that affects your choice of basis sets. And what kind of spectroscopic properties are you interested in? Like if you want hyperfine coupling constants or most power shifts, for example, then you need to worry about the spin density or the charge density at the nucleus, and then this means you need to have flexibility at the nucleus. So you need to have a good match of all these aspects. Now, we said that Hartree-Fock is the fundamental approach, but it's not good enough. Some of the post-Hartree-Fock methods that you might encounter are methods that deal with so-called electron correlation. The electron correlation is the part of the energy that is missing from Hartree-Fock. Hartree-Fock is also called a mean field approximation, in the sense that the electrons do not kind of see very clearly what's happening around them. They see just a blur. So improving the electron-electron interaction, or in other words, recovering the correlation energy or describing electron-electron correlation, is the subject of post-Hartree-Fock methods that will want to improve things. One way of thinking about improving things is to think about these orbitals, and these were like the Hartree-Fock orbitals, for example. But we have also like empty orbitals, like you know about the LUMO, but right, we have other orbitals that were left over from the SCF, from the self-consistent field procedure. So we provided a number of basis functions. We let the calculation do whatever it does. It found the best set of molecular orbitals and put the electrons there. Right? But there are leftover orbitals. So one way of thinking about improving the wave function is to include these sort of excited determinants. So we put the electrons in the unoccupied orbitals one by one, or two by two, or whatever. And we make a linear combination of everything. And this essentially improves. We have many more parameters now. So that's one way of making the wave function more flexible. And that improves things. And when we include all possible determinants for a given basis set, so the number of orbitals that we obtain depends on the size of the basis set that we give. Because this determines how many molecular orbitals we will obtain in the end. When we create all possible determinants, we have the so-called full CI, which never happens. We can truncate the CI to maybe more single excitations, double excitations. We have things like CISD. Or we can think about it in a way of using perturbation theory. So the most commonly used perturbation theory in chemistry is probably Müller-Plesset, second order perturbation theory. This assumes that the reference, which is like your Hartree-Fock reference, is good, and that the perturbation is weak, and then it predicts a correction to the energy. Okay. In practice, it can work, but it really depends on what you're looking at. Since we're talking here about transition metal systems, you have to know that MP2 is not working well for transition metal systems. It's really not working well for open shell systems, and it's mostly inadequate for most of spectroscopy relating to transition metal systems. So that's just something to know. That's not necessarily the case for organic chemistry again. Then we have something called coupled cluster theory, which is based on a reformulation of how we describe the wave function. Okay? You can find all the formulas in the lecture notes. What's important to know is that coupled cluster theory is legitimately and correctly considered to be like the gold standard of computational chemistry. Specifically, the version of coupled cluster theory with singles and double excitations and perturbative triples. When you can do this, you are in a very good place. Okay, you can benchmark other methods against this. It's not perfect, and it's still like it's part of a series. Okay, it's somewhere there, but for many properties, it's considered a very good standard, a reference method at least. And today, with methods that employ the local correlation, such as the DLP&O method, you can actually do pretty big systems, like real molecules. And that's with the DLP&O approximation. Once you understand also like how it converges with respect to different parameters, you can actually treat transition metal systems, like real transition metal systems and metalloproteins, and do really nice stuff with it. Then we have multi-reference methods. Okay, and multi-reference methods that you might come across are mostly of the CASSCF form. We have exercises on CASSCF calculations in some of the practicals. So in CASSCF, we define a complete active space, so a subspace of the orbitals, the Hartree-Fock orbitals, and then we do a full CI in there. Okay, and we also allow the orbitals to change. We do not keep them fixed. So this is a way of targeting, like increasing like the flexibility of the wave function, or correctly describing a very weird electronic situation, but in a very limited space, a chemical space that we define. So it's our choice. Okay, and then this also makes it a bit less black box than anything else, because you can make a weird choice of your active space and you can get weird results, and that's it. So we have these methods, this kind of sequence where Hartree-Fock and MP2 are not really useful for transition metal chemistry, but you should know about them. And then we have the couple cluster hierarchy, and that's quite useful for transition metal chemistry. And then we have CASSCF and related techniques that attempt to recover the dynamic correlation, because CASSCF is also not a method that recovers the dynamic correlation. And these are really useful for specific types of spectroscopy. Finally, just a quick tour of density functional theory, because that is the workhorse of computational chemistry, and it's really one of the most useful techniques also for the spectroscopy of transition metal systems. So DFT as a concept, like it's not it does not fit into what we described, but conceptually it starts from somewhere else, and it deals with the density directly. So the density is a much simpler function of three variables. I mean, you can imagine the density like it's a density. It's just a density, and we can draw it. Okay, we can probe it, we can draw it, and it's a physical object. It's not like the wave function. That is not. And it should be more satisfactory in many ways to use the density than to try to play all these tricks for dealing with the wave function. The reason we can actually use the density to do like full quantum mechanics is that the density contains like practically all information we can require. So if you have a density, then if you study like the density, you can see that there are some cusps. Cusps is like when weird things happen like this. Okay, and this is where there are nuclei in the electron density. So you know where your nuclei are. And then if you study the shape of the cusps, right, you can tell what nuclei are there. You can get the charge of the nucleus. And then by integrating the density, you know how many electrons you have, and that's all you need. Like you have just specified your system. And you can actually fully determine the Hamiltonian of the system by examining the density, but you don't actually need to do that, because the point is that from the density you can directly get whatever you need in terms of energy and other observables, and that's what density functional theory is all about. So density functional theory is saying that it is possible to go from the density to the energy, or something else, using something called a functional. So a functional is like a recipe where instead of a number giving you a different number, you give it a function and it gives you a number. In this case, the function is the density. So you have some sort of recipe and you give it a density and it gives you the energy. And this is based on some theorems, like the first Hohenberg-Korn theorem is that there is something called a university density functional. So that is actually a universal theory. So that is supposed to work this way. And the second theorem is telling us that there is a variational principle for the density. So if we try different densities, then only the exact ground state density minimizes the value of the ground state energy functional. So it gives us a way to think about doing calculations, but it also means that we would try different densities, which is a bit weird. But we're not trying different densities, we're trying different densities, but we are first expressing the densities in terms of orbitals. So we go back to the familiar ground of Hartree-Fock. So we have orbitals. In this case, they're called Kohn-Sham orbitals, and they look and smell like very similar to Hartree-Fock orbitals. But they have something special because they give you a density that is supposed to be much better, which if you feed to the functional that you're using, then you're getting a much better energy. And if you had the exact functional, then you might even get the exact energy. And that's the funny thing about this. So there are all sorts of different questions one can ask about what is Kohn-Sham. Are the orbitals special? Should we be thinking about them the same way as Hartree-Fock orbitals? And is this a really single determinant method like Hartree-Fock, or are we actually having, like, if we have the real density, then it does not matter what Kassasiev is telling us, because that's like a different universe of constructs. Well, these are open questions. What you will see is that there are hundreds and hundreds of different functionals because nobody knows how to approximate the exact functional. So the exact functional does not exist, and there are different ways of trying to create different formulas that might approximate the exact functional in a better way, or in some cases. So one way to approximate the exact functional is to use known limits. For example, there are specific limits like the uniform electron gas, where you have like a uniform density. And then we have some expressions about the uniform electron gas, and we want whatever we construct to converge at the limit to these expressions. So we can have these kind of boundary conditions. So there are different families and different levels of functionals. One is called the local density approximation, where the energy eventually depends only on the scalar value of the density, like what's the value at each point. Or we can be thinking about depending also on the gradient of the density. So the functional takes into account, or the energy depends also on how the density is changing at each point. And then we have many functionals that belong to the GGA, and that was the first useful approximation in chemistry. And it's still pretty good for many tasks in spectroscopy. We can have meta-GGA functionals that include additional components, or we can have hybrid functionals that mix some Hartree-Fock exchange for very good physical reasons, actually. And these are the hybrid functionals, such as the famous or infamous Bither-Lip, and that has been a game changer in computational chemistry. It's still superior than many other methods in many transition metal problems, such as spin state energetics and things like that. Of course, this has also led to the adjustment of Hartree-Fock in order to produce specific results. You might have come across it, or you might actually play with it during the summer school, and there's always a question here whether this is something that is a legitimate practice or meaningful practice, and that's again an open question, or that it depends what you want to do or why you're using it. And in this context, I will remind you of the remarks in terms of the model and the sample and the observables, and, what are we trying to achieve with computational chemistry methods. Finally, there are some range-separated hybrid functionals that have variable percentage of hydrophobic exchange, and they behave much better for specific properties and specific applications that we can discuss. There are also double hybrid functionals, you might have heard about them, that incorporate an MP2 type of component in the whole expression. So you have your hybrid functional, and then you take the orbitals and you also introduce a percentage of MP2 correction, so you do MP2 on these functionals. There is a concept of the Jacob's ladder of DFT. You might have come across it. So it's like the LDA, GGA. Now that's a very useful concept to organize our expectations in general for most of non-transition metal chemistry. So the Jacob's ladder of DFT is hardly applicable to transition metals, to open shell systems, and it's practically not a good guide for spectroscopy. So for example, double hybrid functionals are very, very bad for many transition metal systems, especially open shell transition metal systems. They're very bad for spin state energetics. They're very, very, very bad for most spectroscopies. So that's not their fault. Maybe in principle they could be better, but what is available right now has a problem with transition metals, and that also is relevant for benchmarking that you will find. So you may have a project and what method do I choose? The benchmarks that are available in the literature are not fully representative, let's say, of problems that we might be dealing with here in the summer school. So you do not have extensive benchmark sets on EPR parameters, for example, for transition metal systems or for Mossbauer. That's not because someone didn't work on it. Okay, that's because we do not always have enough data experimentally. Okay, so we recently had a benchmark study on Mossbauer. We wanted to figure out what's the best way to calculate Mossbauer. We collected everything in the literature, and there were 80 examples, 80. That's the complete literature of complexes that had a very good crystal structure and had a very good spectra and were low temperature. That's all. So that's even worse for copper. Like if you have copper systems and you want to find like G tensors, okay? How many are? There aren't 30. There are 20 something with like properly resolved, like high resolution APR. That's it. So it's still a problem, also because we cannot benchmark and then adapt the functionals. So then it becomes a bit complicated to know what to use, and all of these aspects, like how you define the model, what property are you looking for, what method are you going to use, all these are interrelated and they cannot be disentangled. Now, I will skip a few things because they simply refer to the content, okay, of the summer school, and I will just go to the closing remarks. Just as a summary, so the point here is to explore the synergy of spectroscopy and computational chemistry. Some messages I try to convey is that one needs to consider the broader simulation problem and not just what kind of calculation will I do, but there's a broader problem here of like what is my system. We need to keep in mind that a computational experiment, okay, it's not a measurement, and this has certain implications on how we use computational chemistry. There is an embarrassing number of methods, algorithms, and approximations. Maybe no one kind of knows all of them. there is a difficulty in evaluating computational results. You can do something really stupid in the lab, and then hopefully you will not get a result. Okay, or that's usually you don't get something. Unless something is really, really broken technically, in the program, or unless you define things like incorrectly fundamentally, you will get a result. Now, I said some bad things about double hybrid functionals. Now, whatever you do, you will get a result. I said bad things about Hartree-Fock. Whatever you do, you will get a result. But for example, we have recently done a large study of molybdenum compounds. And for all of these compounds, like Hartree-Fock doesn't work. It gives a fundamentally wrong electronic state with spins everywhere. If you take that, you don't look at it, and you do a couple clusters, you will get a result. It will not be unreasonable, but that's not a meaningful thing to do. So most of the times, or unless something is really broken, you will get a result. And that's the dangerous thing about computational chemistry, is that are you doing something meaningful? And you need to look into that and decide for yourself if you're doing something meaningful, because a good number does not guarantee that what you did is meaningful, or a good looking number. So yeah, the final point is that, and that's the point of the summer school, I guess, here, is that there is no supremacy of energetics, and that the calculation of spectroscopic parameters is a more complex, but at the same time a much more rewarding activity. And I guess we'll have many, many examples of this. So I guess that's the end of this lecture. So thank you very much.